Welcome back to ECE 320A. Homework number 9 is due the next time we meet, and homework 10 is a week from today, which is our last time that we will meet as a lecture. And our final exam is 2 weeks from today. What you will want to pay attention to is the start time of the final. The final is starting at 10:30 and going until 12:30. So make sure your alarm is adjusted appropriately for the final exam, which is on Tuesday, the 8th of May. What I want to do today is get into filtering, which is chapters 14 and 15. We already now know, I hope, a little bit better on frequency response, how we can sketch those, and once we know where frequency responses are breaking or bending, we now know where poles and zeros are located, and we could actually create a transfer function to realize a given filtering behavior. Once we do that, then we can realize that shape in a circuit. And we'll quickly look at some passive realizations of the 4 different types of filters. Then we will move into active filters, which we've already analyzed in terms of transfer functions. We'll look at, or maybe make a couple of comments on why we might be interested in active filters. We'll work through an example. Then we will talk about scaling, which allows us now to design these filters for maybe a nominal bandwidth of 1 radian per second. And now if somebody says, oh, I really want a low-pass filter with a bandwidth of 10,000 hertz, we can now scale that 1 radian per second low-pass filter to have a bandwidth of 10,000 hertz. And obviously I'm using 2 different frequencies, radian per second and hertz, and you need to make sure that you're consistent with those terms. We can also scale the magnitude of our frequency components, or the R, L's, and C's. We can change those to give us a better magnitude. If we know Josie's going to give us a 0.1 microfarad capacitor, then we scale our circuit such that we're using 0.1 microfarad capacitors, and the remaining pieces, the resistors, for example, will now be adjusted so that we can still realize this 10,000 hertz low-pass filter with 0.1 microfarad capacitors. That's what the scaling allows us to do. Here's today's in-class participation, which pertains to reviewing for the final exam. And I would like for you to write down on a piece of paper what concept or topic or problem you would like reviewed prior to the final exam. And I'm trying to figure out how I will do that. Maybe if there's a handful of topics that sort of rise to the top that people would like to see, maybe I'll make 5 little videos discussing those. I don't know if we will be able to coordinate with your schedules and my schedule a review session, unless you think that would really be helpful. But we'll see. So give me your thoughts on what you would like to see reviewed for the final exam, and then I'll see if I can maybe put that together in some effective form. After we look at frequency scaling and magnitude scaling, we'll look at a particular example of a low-pass filter using those concepts. Then we will talk about Butterworth filters. So I hope everyone brought their flapjack turner and some syrup so that we can do some filter design, Butterworth filter design. And Butterworth filter design means what? Flat, maximally flat. And hopefully we'll be able to comment on that when we get to that location. meaning all the poles are not necessarily going to be real. If you have one pole, two poles, three poles, and we'll talk about order of a filter, but I think you already know what the order of a filter might do. If you were thinking of a low-pass filter and somebody said, oh, I want a first-order low-pass filter, and somebody else says, oh, I want a second-order low-pass filter, what is the distinguishing feature? Obviously, it's the order, but if you were looking at the Bode plot, how could you determine the difference between those two filters? The slope in the roll-off range from the pass band to the stop band is going to be much sharper or steeper for the higher order filter. It'll be twice if it was a first order versus a second order. The first order will be rolling off at minus 20 dB per decade. The second order is twice that. It's now minus 40 dB per decade. Meaning we may want a very sharp transition which says, oh, I need a sixth order Butterworth low-pass filter. That means that we have 6 times minus 20, or minus 120 dB per decade, and so you're rolling off quite rapidly with a sixth order filter versus what you would roll off in a first order filter. And hopefully that will become more clear as we go through this material. Let's start with a very general overview of chapters 14 and 15. We've already been dancing around in those chapters anyway, so let's go ahead and say that we're working there. We've now been dealing, or what I would like to think, we've now become a little bit more comfortable with the frequency response. And if you aren't yet, hopefully after homework assignment 9, you're a little bit more comfortable. This frequency response information, or the information that the Bode plot provides, that's actually very helpful in helping us understand different filtering behavior, or different types of filters. The frequency response information is helpful in understanding the particular characteristics of filters. And let's just look at 4 basic types. And we can actually think our way through those in terms of passive circuits to realize these kinds of filters. The first filter is a low pass. And what does that look like in terms of its magnitude response versus frequency? If I had to sketch that in a straight line approximation, hopefully everybody's comfortable with that sketch. If I said, sketch me a low-pass filter, you better be able to do that for the final. What would you draw? Now you just have to draw 2 lines. They can be straight. One can go here, and another one goes there. And if we were looking at this in terms of a passive circuit, we could now think of this transfer function between the input V sub I and the output VO of this simple RC circuit would provide this kind of a shape, where this point, the break frequency, is 1 over RC. This is a first order low pass filter, and we may want to have a low pass filter if we had high frequency noise. We could help remove that or reduce the impact of that noise. And another thing is we could say, well, that's going to also help us reject high frequencies. And if you start doing signal processing with digital signals, you may actually want to pre-filter your waveform before you actually sample it, and that's what would then be referred to as an anti-aliasing filter, and you would want to have that break frequency selected such that you are throwing away frequencies above, let's say, the Nyquist frequency. And that would then be helpful in not having high frequencies actually after sampling look like low frequencies. So think of your old westerns and the wagon wheels spinning. Sometimes those don't really look like they're going forward. That's sort of this idea of aliasing. Things are looking differently than they actually are because of the way that the system is being sampled. An alias in frequency, you might have a frequency that's actually at 20 hertz, but it gets aliased by the way that you've sampled, and now it's actually appearing like it's 4 hertz, depending on how you've sampled or what you've done. So that's what the aliasing is referring to. That's one type, which we've already really talked about quite a bit. Let's look at another type, which is just sort of the opposite of the low pass, and that's the high pass. In this case, again, we have 2 lines, and let me just create this one out of a slightly different circuit, where now let this be R over L, and my circuit now that would allow me to favorably pass high frequencies versus low frequencies between the input and the output in a passive circuit would be this RL circuit that I've just sketched. So now if you find the transfer function between V sub I and V sub O, and you could do that by a voltage divider in the frequency domain, you convert this to an S domain circuit, and you now have SL over SL plus R. And now you can see that that S in the numerator is giving you this slope coming up from low frequencies, and then you break it off at that pole location, which is the determined by SL plus R. Question? So now, in terms of high frequencies, what's actually happening? Now, if you looked at the transfer function, you have SL over SL plus R. So now as S goes to infinity, the bottom and the top are going sort of at the same rate in terms of getting large, and so they're becoming 1. So now at high frequencies, what does this inductor do? Its impedance gets really, really big, doesn't it? SL. So if this gets really, really big, you could think of that basically disappearing in a sense. It becomes just air, and now you have V sub I and V sub O, and if there's no current flowing through this resistor, they're exactly equal. It's the same voltage. So that's another way of sort of thinking about it in terms of the circuit behavior process. Yes?
So both of those, both high pass and low pass, are low pass and RL high pass. If you just switch the signal voltage over the other element, wouldn't it become
so now, essentially, I showed you these two to contrast. So the question was, what happens if you flip-flop the R and the L, or the R and the C, in the 2 circuits that I've provided, and you will get the opposite behavior. In the original low pass, you flip the location, or if you measure your output across the resistor versus across the capacitor, you'll get the opposite of the low pass or a high pass. And that's one reason why we actually are going to concentrate most of our effort on low-pass filter design, because now you can create high-pass from low-pass by simply replacing the S's with 1 over S's in your transfer function. And now you've mapped this low-pass behavior into a high-pass behavior. Does that help with your comment? So the comment was valid. You can, and that's what I'm hoping that you guys are all starting to become a little bit more comfortable with, is this circuit analysis and the explanation and the sketching of the circuit, or I'm sorry, of the frequency response. Meaning if now somebody gives you that frequency response and they say, I want that break to occur at a particular frequency, now you can give them a circuit that will provide that kind of a response. That's what I'm hoping we're moving towards. In this high-pass filter, we are now maybe rejecting low frequencies, is why we want to make that design happen. And why would you want to do this? Well, maybe there's a DC offset that you want to throw away, or at least reduce its impact on your circuit. So now you can reduce the DC bias or offset in your signal, for example, by high-pass filter. The next filter that we will talk about is the bandpass filter. And in the bandpass filter, what we are wanting to do is actually pass, let's say, intermediate frequencies, or maybe somebody has a communication signal that you could care less what's happening at low frequencies or high frequencies. You know that communication signal is at a particular frequency. Let's just isolate on that frequency. This might be helpful in communication signals. If that's the case, I think you can now anticipate what the shape of the frequency response is going to be for a bandpass filter. And we've, I think, already sketched some of those. We want to basically reduce the influence of low frequencies. We want to pass intermediate frequencies, and we want to get rid of high frequencies. That could be a generic straight line approximation of a bandpass filter. And what do we see there? Well, we see a couple of breaks, don't we? So we know we have to have more than one frequency in the denominator. And now just one way of realizing that, let's say, is by means of an RLC circuit. And hopefully you can convince yourself, either maybe not now, but later, that if you find the transfer function between those inputs and outputs with the appropriate choices of R, L, and C, you can create this bandpass behavior or bandpass structure, which favors passing intermediate frequencies. The opposite of that is the final one that we will look at. And instead of passing frequencies in a particular band, let's reject those. And in this case, something that you might be wanting to reduce or try to get rid of might be a disturbance that you know is present in your particular circuit or system, and maybe it's a hum due to the... I'm sorry? Maybe. I know, everybody else got it, but I sure didn't. That went right over. I have no idea. So what does this look like? in terms of a frequency response, now we have something like this. We're trying to reject or get rid of intermediate frequencies where you can determine what that is. Maybe it's 60 hertz, and you want to retain low and high frequencies. Now we could have the same kind of collection of elements, but we want to now work with a different combination or pickoff point in that passive circuit in order to make that become a band reject filter versus a band pass. And here we're essentially pulling off information from the two that we weren't pulling information off of in the band pass filter. So this, is, in a sense, is like the opposite of what we were doing with the band pass, or a dual type concept. Are there questions on these four types of filters and their frequency response? If I gave you such a diagram and said, oh, here's the magnitude of a given filter, can you now find the H of S associated with that magnitude response? What do you know is happening at low frequencies? Here's the low frequency, and what gives you that, and let's say that it's always coming down, it's never flat for low frequencies. That now corresponds to a pole at the origin. So now we have a pole at the origin. What's going to allow us to go flat? A zero, because now that's reducing our slope, and now we want to reduce it even more or make it go the other direction, and we put in another zero. So there are ways of cooking these up in order to create different filtering behaviors. Well, we would then have to determine what our circuit looked like. So the question was, what are those points? It's going to depend on how we build this in our circuit in terms of those break frequencies. But if you were just asked to find the transfer function, you should be able to find that without worrying about how am I going to realize that or make that, create that with a circuit. Question? The question was, what if we start looking at the different combinations of pickoff points, I think. What if we looked at the voltage across the resistor and the inductor, or maybe the resistor and the capacitor, if we ordered those a little differently? And there I would just say, look at your napkin, or go home and pull out one of your napkins and just see what you can find, or it will depend on the particular parameter values, but that may give you a different relationship between these break frequencies and what's happening, and maybe you won't have a pole at the origin, etc. So you'll just have to sort of experiment with that, and I don't play with this that frequently to where I could say, oh, well, that's obvious that you can just put this there and that's going to happen. So there's not that many combinations that you can look at, but once you know how to apply a voltage divider, which is really all we're doing, you can analyze all the different possible combinations of inputs and outputs relative to the connections, interconnection structure. Yes? It's just however you set it up in terms of, so the question was, is that just this difference between the applied voltage and some other output signal? It's however you want to think about it, really. And what you are pulling off, or how you've now decided on a given waveform. But what you will have is if I now said, oh, I have a current going through that circuit, what do you know the denominator of that transfer function? How does that compare with the denominator of this transfer function between V sub I and V sub O? What have we talked about? Final exam review question. If I ask you what's the denominator polynomial of this transfer function, how does that compare to the transfer function between the input V sub I and the current I? What? Pardon? I couldn't filter that out. I needed a spatial filter because it was coming from two different directions. The zeros of the the zeros of the denominator are the poles, right? So if you look at the denominator, but what did we learn about transfer functions in the general sense? If I give you a circuit, and now maybe somebody says, oh, I'm really interested in the voltage across the resistor. So they call that V sub R, and that's my output. Somebody else says, no, my output is the current I. We're all keeping the same input, V sub I. Somebody else says, oh, no, it's V sub O as it's indicated. What do you know about the denominator polynomial in those three transfer functions? It's the same. So our poles are the same. Once we've selected R, L, and C, those poles are fixed. That's what I was trying to ask or get as a response. Other questions on this? And this is now just passive. Let's now move into chapter 15, which is active filters. And now let's pretend we are 2 years old. Why? Why do we want to work with active filters? One is we can actually implement these or provide implementations that do not contain any inductors. And we can make bigger order circuits that don't require inductors. So let me say they don't require inductors. And why is that an issue? Pardon? Inductors are bulky, aren't they? And we're all worried about the biggest loser or something. No, sorry. So we wouldn't have to carry that around, or if we were launching it into space, we wouldn't have to worry about the weight of those inductors, right? So these inductors could be bulky or heavy, and maybe they're expensive actually. Because now we have to get this core and we have to wind this magnetic wire around the core, so we have to build these inductors, and maybe that's more investment than we want. If we can just have some op amps, some capacitors and resistors and put those together, maybe that will be easier. That's, pardon? And they are going to, well, we know Eli is going to be there, right? If we have the inductors, and that may or may not be what we want to be living with, but we can essentially reproduce that behavior with R's and C's and op amps with active devices. So we can sort of create these inductor type systems with active elements. Obviously the inductors are passive, so if we didn't want to energize things, that would maybe be okay. But also these active devices may allow more control over how much amplification we can introduce into this filtering behavior. They allow more control over the gain or the amplification that we have. And dealing with op amps, we can maybe not have as much impact of loading. or our circuit that we now connect this to may not load us as much. So these active circuits will allow their characteristics are not altered by the loads at their outputs. And I'm not going to go into the basics of op amps. I'm going to assume that we know that, and I guess according to some of your fellow students that are interviewing, apparently that's a popular question, is to ask some op amp question. So now you can impress your interviewer by sketching some filtering circuits, for example. Maybe, and in the particular interview, apparently what they were asking was, sketch me an op amp circuit or something as basic as that, and the student said, would you like to have that an inverting op amp or a non-inverting op amp? And I think that was sufficient impressive response to hopefully get a second interview. But we will do better than that. So you could now look at problem, I think I tried to find this, 33C on page 599 of the textbook, and here's the circuit. We have a resistor and another resistor, then we have a capacitor. That's going to go into the inverting terminal. The non-inverting terminal I'm going to connect to ground. There's my output, and that's measured relative to that same reference ground location. And let me make this a capacitor. Now I'm going to do something that you need to kind of keep track of. I'm going to now short that node between this resistor and the feedback path, which I'll label R sub 3, and these two capacitors, 1 over SC, 1 over SC. Those are the same size capacitor. Here's R2, here's R1, and let me call this V sub I. And I'm interested now in the transfer function between the input voltage V sub I and the output voltage V sub O in that particular circuit. Yes? Yeah, but now we're going to get, essentially, we now want to have two, or, yeah, it's basically giving us a factor of 2. But now this is just a made-up problem for you to analyze. This is problem 1533C, and you maybe won't have to do it, or if I assign it, maybe you can work it if I do it properly now. So how do you analyze this, or what would be one approach to this? You could now say, here is, let's say, node number 1, and I'm going to call this voltage V sub 1, and let me call this my N node, and I can now write or apply, and really this is this entire point, so my node is a little bit bigger. Now I can do a KCL at those two locations to try to find a relationship between V sub I and V sub O. If I now do KCL at 1, I have V1 minus VI over R1. I have V1 over R2. I have V1 over 1 over SC. So let's just say that's this one going in that direction, and that's connected to ground virtually through the op amp, because I'm now with a negative feedback configuration. I'm feeding the output back into the inverting terminal of my op amp, and now I could look at this current, which is as just commented on, the same as what I had before. So now maybe the sizing of your capacitors is why you need to split them and not have one that's a bigger size, for example. This is now all of the currents leaving node number 1, and those sum to 0. If you put all of those together, you end up with 1 over R1 plus 1 over R2 plus 2SC. There's the combination of your capacitors. That's V1 is equal to 1 over R1 V sub I. And if we now solve that for V1, we end up with something that looks like R sub 2 over 2R1 R sub 2 C times S plus R sub 1 plus R sub 2 V sub I of S. And that's now the transfer function between V sub I and that intermediate node that we called 1, V sub I. And now can you sort of see what this might look like as a frequency response between V sub I and V sub 1? Or what do you know is true in that particular transfer function? What's the order of that transfer function? It's first order, isn't it? You had 2 energy storage devices, but somebody let the cat out of the bag and already gave it away, that those were in parallel. That's okay. So it essentially came down to one effective capacitor. So we have a first order behavior between V sub I and V sub 1. And if we have where is that pole located? Well, you don't know, but you could find it, right? You set the denominator equal to 0, and that will give you your pole location. And what does that tell you? What's going to happen? What's your DC gain between V sub I and V sub 1? R2 over R1 plus R2. So it's some constant, isn't it? You're going to be flat at low frequencies between V sub I and V sub 1. Then what happens? So now we know we're flat in our frequency response, and this is just an intermediate frequency response. Once we hit the pole, we start going down, and we go down consistent with the first order denominator at 20 dB per decade, or 6 dB per octave, a factor of 2. That's one KCL. Now we need to relate V1 to V out, and we can find that relationship by performing KCL at N. And doing that, we see that we have the 2 currents going, let's say, in the opposite direction, or maybe we keep them going in the same direction. So let's just say the sum of the currents going into that node, and now we have those 2 blue currents and this current, and those 3 will sum to 0. And that will now allow us to relate V1 to V naught, or V out. And the 2 blue currents now say that we have V1 over 1 over SC plus V1 over 1 over SC. And we have our red current coming in from the right, and that's now V naught, or R3, from V naught to ground. So we now have V naught over R sub 3 is equal to 0. If we now solve this for V naught, we end up with minus 2 R sub 3C times S V1. That's our relationship between V1 and V naught. We already know what VI to V1 gives us, and now we can concatenate these different relationships to actually find our transfer function that says V naught is now minus 2 R sub 3 CS. Oh, and there was something else up there too, wasn't there? Wasn't there an R2? So we now have minus 2 R sub 2 R sub 3 CS. We have R1 plus R2 plus 2 R1 R2 C times S. And that is our transfer function between V sub I and V sub O. Now, maybe that looks a little bit ornery, but suppose we simplify it by going to Josie and say, can you give me, and now you'll just have to excuse the units, they will be okay. I'm just going to numerically set those equal to 1. So your capacitor is not the same as your resistor. Hopefully you believe me on that one. But this is just a shorthand way of saying put all of those parameters equal to 1. If I now replace all of those R's and C's with 1, I now have V naught of S over V sub I of S equaling minus 2S over 2 plus 2S, or a transfer function that's minus S over S plus 1. And what do you see now in that transfer function? Now these poles and zeros are pretty easy to locate, aren't they? We have a 0 at the origin, and we have a pole at S equal minus 1. Maybe I should do another in-class participation and say, what's the Bode plot of that look like? But that should just be a gift, is it? If I ask you to sketch the Bode plot of that transfer function, could you do it? What's happening at low frequencies? Or what's the DC gain? Does it exist? So what is my DC gain? 0, isn't it? The denominator is well behaved. I can't divide by 0, but in this case I'm not going to have to. If I set S equal to 0, my denominator is well behaved, it becomes 1. My numerator vanishes, so my DC gain is 0. At low frequencies, I am not passing anything. At the extreme, at DC, at constant frequencies, at a constant frequency, there's nothing being passed. What happens then, or that gives me then this sloping line coming up from the bottom. And how fast is it coming up from the bottom? What's my slope? And now, where do I join that with the flat line? Because I do have a pole that kicks in. That pole kicks in at 1 radian per second. That's my magnitude of H in dB. And this is now as a function of frequency. What's my phase curve look like? Let's say this is 0 degrees and this is my omega axis. Now maybe it's a trick question. What do I have here? I would probably pull this into not 2 pieces, but 3 pieces. I would factor out the negative and say that's a -1 for my constant piece. Then I have a 0 at the origin and a pole at s equal to -1. What does that tell me? What's the -1 look like in the phase? The -1 did not impact my magnitude at all, did it? Because I'm just throwing it away when I do the magnitude of the numerator. But in the phase plot, where does that occur? Let's say these lines are now 90 degrees apart. What's my constant term going to produce as far as an angle? What did I say? The constant term is -1. What's its angle? What's the angle of -1? If you now had to sketch -1 in the complex S-plane, you would say, oh, that's that point over here at -1. So that has a length of 1 and an angle of -180 degrees, and I'm going to be negative again, okay? So you'll just have to tolerate me for the rest of the semester on my negativity, but that's now -180. That's the constant piece. The constant piece is now here. And that's for all frequencies. I'm going to say this is -90 and this is +90. What's the 0 at the origin contributing? What's its phase? So now you replace S with j omega, and now you're looking at the angle associated with j omega. So I have a 0, I have a thumbtack in the S-plane, right at the origin, and now I'm walking up the imaginary axis, and I'm actually wanting to look in the positive real direction and have my angles determined from that location. There's the origin. What's the angle from that point up to me? So if I was down here at the origin and I needed to look up at j omega, what angle am I turning through? 90 degrees. What if I go up a little bit further on that axis? What angle do I turn through? It's not changing, is it? It's always 90 degrees. The angle contributed by that 0 at the origin is 90 degrees. So this is the 0. This was due to the constant. I only have one more piece to worry about, and that's the pole piece. And what do I know about the pole piece? We have to worry about that one turning on and turning off, don't we, in terms of its slope? Where does it, and how much phase will it ultimately contribute, that pole? It'll give us 90 degrees downstairs, so it at most will give us -90 degrees at high frequencies. What's it giving to us at low frequencies? S plus 1, or j omega plus 1, and j omega is very, very small. The angle of 1, 0. So now we're transitioning between 0 and -90. How long do we agree in our straight line approximation that change from 0 to -90, how long have we agreed that takes? 2 decades. And where do we center that 2-decade transition? Right at the break frequency. So we need to turn it on a decade before, turn it off a decade beyond. And a decade before, now we have to be a little bit more particular on this. Let's say that now we are 10 to the 0, 10 to the -1, and 10 to the 1. Now our pole at our pole at 1 turns on phase-wise at 0.1. It turns off at 10 when it's contributed minus 90 degrees. So now I connect this with a straight line. I have three pieces now to add up, frequency for frequency. Does everybody understand where those three pieces are coming from? This is now due to the pole at S equal minus 1. I look back far enough to the left so that everything is somewhat well behaved. And I say, okay, I have 90, 0, and minus 180. And now here's why you learned your math. So that you can add. 90 minus 180. We start here at minus 90. Where should we end up in terms of our angle? Minus 180, right? Because of that minus sign. If we didn't have that minus sign, if it was a positive, we would expect, since the numerator degree is the same as the denominator degree at high enough frequencies, those angles are going to cancel and we'll be left with 0 degrees. In this case, we're left with minus 180, and we should be there by that point. And we'll then transition between those. Whoops. You can sketch better than I can. I'll probably missketch again and err on the other direction, but that's now our phase curve that we have for that particular filter. But I'm sorry? Yes, and so that line is supposed to be parallel to the pole's sloping line because that's the only slope that we had. All the others were constant. That particular, remember what we started with? We started with this guy. And we simplified it by putting all of our parameters to have a value of 1, and now somebody says, that's pretty boring. And they say, can you change the behavior? Can you change where that break occurs? Maybe we like the fact that it is giving us what were we ending up with in terms of our frequency response. That's based on the magnitude. We have a high-pass filter behavior, but we don't want a 1 radian per second frequency for the cutoff. Maybe we want that to be different. And maybe we're not happy with a 1 farad capacitor. We need to change that. Josie doesn't have one of those yet. Okay? She doesn't have one for safety purposes, possibly. Okay? So we don't have that 1 farad capacitor. A few years ago, you couldn't even talk about that. You'd be thinking, oh, the size of a football field. But now they have supercapacitors, and they do exist. But we want to now change that frequency, or break. That's going to lead us nicely, I hope, into this question, which is the following. How can we obtain the passband frequency that we want while using, or let me say while still using, component values that are available to us in the stockroom, that we have available. As an example, suppose I want to use ten microfarad capacitors. Well, this is begging us to go into the next topic, which is concerned with frequency scaling and magnitude scaling. Let's now look at what that means. Suppose now that I wanted to scale the impedance magnitude. And what I will probably do is let me say that the subscript 1 corresponds to my initial value of the impedance, and subscript number 2 is my final value of the impedance. And now I want to scale the impedance magnitude. What I'm saying is I want my scaled impedance, Z sub 2, to be some multiple, positive value multiple of Z sub 1. And now all we need to do to relate that to R's, L's, and C's are simply to remember what our impedance formulas are for R, L, and C. The impedance of a resistor, which says now if I have Z sub 2 is equal to K sub M Z sub 1, if somebody says, oh, I want you to scale the impedance by a factor of 1,000, and if R1 was 1 to begin with, now you're going to end up with your scaled resistor being a 1K resistor. Is that making sense? What about the inductor? What does the inductor look like in terms of its phasor form of its SL, but now we're worried about its frequency response. So now we want to replace S with J omega. Now we want the impedance to be in the form of J omega L, which if we now say that Z sub 2 is K sub M Z sub 1, now we have J omega L2 is equal to K sub M J omega L1. And a lot of these pieces now cancel. The J's cancel, the omegas cancel, and we're left with now L2 looking like the same scaling that we had for our resistor, K sub M L1. Doing the same thing for our capacitor, now we have on the left 1 over J omega C2. That's now K sub M over J omega C1. And we could rewrite that if we wanted to, I guess, as 1 over J omega C1 over K sub M, so that now we can immediately compare the C2 location in both, and we now see that if we want to scale the capacitor by the same magnitude, K sub M, we now take C1 and scale it by K sub M in the denominator. That's now the magnitude scaling of our 3 circuit element parameters: resistors, inductors, and capacitors. That's how they scale in terms of magnitude. Let's now look at how they might scale in terms of frequency. By this is going to allow us to change these 1 radian per second bandwidths to whatever bandwidth we might want. So that's why we want to be able to frequency scale. Here what we want is we want our impedance at the final frequency or maybe what I should say is the impedance at the final frequency equals the impedance at the initial frequency. So what's R2 and R1 look like, or how are they related by our, oh, and let me just say that suppose I'm going to use omega sub 2 is equal to k sub f omega sub 1. That's how I want to scale my frequencies. I want the final frequency to be a multiple of the initial, and the factor relating those is k sub f. How will R sub 2, my final resistor value, be related to R sub 1? The impedance is not a function of frequency, so we would expect that when we frequency scale resistors, we don't do anything. That's why we need to magnitude scale if we want to change resistor values. Frequency scaling won't do anything. Let's now look at the inductor. So the inductor, Z sub 2, is J omega sub 2 L sub 2. And we've already defined omega sub 2 in terms of the original frequency omega sub 1 as k sub f omega sub 1. That's L2. But we wanted Z2 to equal Z1 at the two frequencies of interest, and Z1 is J omega 1 L1. And now we need to relate those two relationships to obtain our relationship for how we scale the inductor with respect to frequency. The J's cancel, the omega 1's cancel, and if we solve in terms of L sub 2, we now have L sub 2 as L1 over K sub F. Now let's look at the capacitor. Doing the same process, this is now J omega sub 2 C2, but omega sub 2 was just K sub F omega sub 1, but we want that to equal Z1, but Z1 is 1 over J omega 1 C1. Which, if we compare those, the J omega 1's cancel, and we now have C sub 2 is equal to C1 over K sub F. And that's now how we scale our frequencies. I'm sorry, our capacitor with respect to frequency. If we combine both of those scalings into one step, which we can do, so we can now say the two scalings can be combined. Now we know that the R2 is just going to be scaled by the magnitude scaling. L2 is K sub M over K sub F, L1, and C sub 2 is C1 over K sub M, K sub F. And those now are the scalings that we have if we want to magnitude and frequency scale all in one step. Let's now apply that to a particular design. Let's say that now we want to design a first order low pass filter, and we want the bandwidth of that filter to be 100 hertz. We want to have a gain of 2, and we want to use a 1 microfarad capacitor. So that's now what we want to do. We want to have a 100 hertz low pass filter. We want to use a 1 microfarad capacitor. And in the pass band, we want a gain of 2, an absolute gain of 2. What we can do is we can now find an active circuit that allows that to happen, and that's the very first circuit in Chapter 15. And that looks like the following op-amp configuration. We have R1 going in, and in the feedback path we have R2, but we know that's not going to be sufficient, right? Because what would that give us? That's going to be an inverter, so we need to do something that's a little frequency dependent, and if we put a capacitor in parallel with that resistor, we'll have a better success rate at finding or designing a low-pass filter. In this case, we can now think of V out over V in is minus the feedback impedance over the input impedance. And what is the input impedance? That's just R1. The feedback impedance is whatever I called that resistor, R sub 2 in parallel with C. And we're dealing now in the S domain to get our transfer function to work with. So now we have R2 1 over SC over R2 plus 1 over SC. And if we clean that up a little bit, we have S R sub 2C plus 1 and R sub 2. That's Z sub F. If we combine that, we now have V naught of S over V sub I of S is now equal to minus R2 over R1. That's the ZF over ZI part, and I'll just keep track of the denominator, S R sub 2C plus 1. To get us started, what if we simply said, well, what if we made all of those numerically nice? If we just let them, question? How far up do I need to scroll? Now hopefully you can see that I have this, well, what's my DC gain? It's hidden. But now my DC gain from that is minus R2 over R1. Well, how would you have a positive gain? Or what if you wanted a positive gain? You could put another inverter, either on the output or the input of this circuit. So you can get rid of that, and you may want that for buffering purposes anyway. So now you hang another, so we're not going to worry about that. We'll just say, let's forget about the sign, and we now have R2 over R1 over SR2C plus 1. If we want to change that sign, which it's right now negative, we could by adding another inverter stage to that. And the inverter stage could actually help us with gaining if we wanted to. If we now look at R1, R2, and C being equal to 1, this now becomes, let's just, how about if I say that? If I neglect the minus 1, what's Z sub F over Z sub I? 1 over S plus 1. And if anybody misses that frequency response on the final, they may fail the course. This is now H of j omega, if I want the frequency response. And now I have that I want to sketch, or what do I now know? I now know that my cutoff frequency is 1 radian per second, and H of J0, which is my DC gain, is 1. And that's not meeting my original spec, is it? I wanted a cutoff frequency of 100 hertz. So make sure you're clear on whether I'm talking radians per second or hertz. Here I wanted 100 hertz, and I wanted a passband gain of 2. And if this is a low-pass filter, my passband gain is what I'm going to say is what I have at DC. And our capacitor needs to be something that I didn't assume here. I assumed it was 1 farad here. I need to somehow change that to be, whatever I said, 1 microfarad. So I need to do a couple of things. First, I need to scale that frequency. So I need to find this K sub F, which is really omega nu over omega old. What's omega nu? And that's NEW, not the Greek letter mu, or nu. Sorry. So this is 2 pi times whatever our cutoff frequency was, which was 100. And our old was 1. So now we know that we have 200 pi. Wow, all I can think of now are apple and cherry. But, sorry. Any fruit pie would be fine. So now we have 6, and I'm guessing that most of you have pi memorized to a few hundred digits by this point in the semester. Your calculator does? I'd like to see that if it's 100 decimals. Anyway. 628 is what our frequency scaling is, but what did we say? We needed a capacitor, didn't we? Use the required cap value and K sub F to find K sub M. Meaning, what was our relationship between new and old capacitors? Now we're going to use this magnitude scaling to make things right. We knew that C sub 2 was C1 over KF KN. So now what was, and this was new, and this was old. We know K sub F, that's 628. We don't know K sub M. We know C sub 2, the new. The new needs to be 1 microfarad. C old was 1 farad. Let's now solve this for K sub M. And now we say that we have C1 over K sub F C2. Or this is now 1 over 628.3, and C sub 2 was 1 times 10 to the minus 6, or the magnitude scaling of the impedances will be 1,591.6, and I will let you use up a couple of napkins before Thursday to tell me what the circuit looks like when we meet up on Thursday. Please make sure and hand in your